Actually, the chapter name is analytic function. Actually, to discuss this analytic function, we have to first of all define the complex function. Then we can define limit, continuity, and differentiability of a complex function. So connecting to complex variable, we have to define limit, function, and continuity. We must know x plus, if x plus iy, that means z equals to x plus iy, is a complex number, is a complex variable, is a complex variable which is denoted by z, then f w equals to f of z is a complex function. So if we denote this, z is the variable, then w is called complex function. And this w can be written as u plus ib, because this is the whole function, and this function can be denoted by u plus ib, where u is the real part and b is the imaginary part. And this complex function can be represented as a polar form. You must know from complex properties of complex number, and we can express it as a exponential form, okay, in polar form and in Cartesian form. There are three types of form of complex number. So now, what is the limit of a function of a complex variable? So what is the limit of a function of a complex variable? Limit of a function of a complex variable. The definition can be written as the function f of z defined in the function f of z defined in some neighborhood of z naught is said to have limit w naught at z naught if epsilon is greater than 0, then there exists del greater than 0, which is very, very small and positive, such that f of z and w naught, the distance between f of z and w naught is very, very negligible, epsilon, whenever less than del. This is the actually deleted neighborhood. So that is, in short form, we can write the limit as like this. Limit z tends to z naught, then f of z equals to W naught. And we can figure out, so there are two types of plane. One is Z plane and another is W plane. We can draw the graph for each plane. Suppose there is a circle with neighborhood and Z naught, and another one is, suppose this is the W naught, and this is the W plane, and this is the W plane, and this is the Z plane. So, and this radius what? Del, and this radius what will be? Epsilon. Okay. So this is the imaginary axis and this is the real axis. This is the origin, this is the real axis, and this is the imaginary axis, because it is a complex variable. So for every epsilon, we get a positive del. That means distance between f of z and w naught is very smaller but positive when this condition is satisfied. That means the distance between the point, this is the functional difference. Okay, this is the functional difference, and this is the point difference. So point difference z minus z naught. There are many z values, but z naught is the center. So if we take the distance between every values of z from the center, and it will be less than del, then we get this condition. Functional difference will be epsilon greater than epsilon less than 0, and which is very negligible and positive. Understand, everybody? So first of all, what is complex function? If z equals to x plus iy is a complex variable, then w equals to f of z is a complex variable or complex function, and it's denoted by u plus ib. Remember it. U is the real part and b is the imaginary part of complex variable or complex function. Now, what is the limit of a function of a complex variable? So we are defining limits in terms of complex variable. The function f of z is defined in some neighborhood of z naught. Neighborhood means what? Just if we center z naught, then we can draw any circle, and it is called actually neighborhood. This is the neighborhood, and this is another neighborhood in w plane. So z naught is said to have limit w naught. F of z will have w naught limit at z naught if epsilon greater than 0. Epsilon is very near to 0 but very small. Then there exists del greater than 0 such that the functional difference less than epsilon will be happen whenever point difference will be what? Less than del. In symbolically, mathematically, we can write limit if z tends to z naught, then f of z will be tends to what? W naught. And we can draw, this is the z plane for every value of z, and this figure will be this, and this figure will be what? W plane. Okay. And center is what? Z naught, and in W plane, center is what? W naught. The function f of z of a complex variable z is said to be continuous at the point z naught if for any given positive number epsilon we can find another number del such that the functional difference will be very negligible but positive, which is less than epsilon. Whenever, for all satisfying z, the domain z minus z naught, that means point difference will be positive and less than del, where del is very small positive number. Remember it. So that means limit exists. This definition is the actually I have written limit definition. Then f of z is said to be continuous at z equals to z naught. This point at the point z naught, that means at the center of the of what? Z plane. Then the limit will be the equal to the functional value of at z naught. Okay, f of z naught. Another condition is applied here. for continuous. This definition will be for what? Limit, but another condition is imposed for what? Continuity. Okay. Now, what is the actually differentiability? You must know about that from the differential calculus. We defined what is differentiation, or what is the geometrical interpretation of differential calculus. But the differentiability same concept, but it is in complex variable, and you have to define it, and you have to take the function as a complex variable. Let f of z be a single valued function, complex function, of course, of the variable z. Then the first differentiation of f of z can be written as limit del z tends to 0, then f of z plus del z minus f of z divided by del z, provided the limit exists and is independent of the path along the which del z tends to 0. Let P be a fixed point. Suppose there is a point P, and this is the geometrical interpretation. P is the limit, P is the point, and another point is what? Q. Suppose their functional value is Z. Okay. So at Q, functional value what will be? Z plus dz, right? Z plus dz. Now, the functional difference what will be? Functional difference f of z plus del z minus f of z. This is the difference, and this difference means actually along the y-axis. This difference what? Along the y-axis. That means what? Perpendicular. Okay, perpendicular. And del z difference what? Along the x-axis. This is the del z point difference. So perpendicular by base what? In trigonometry, tan theta. So this tan theta means what? Slope. Slope of the slope in geometric interpretation. Okay. So in physical interpretation, we can define the differentiability as limit del z. If del z tends to 0, then we get a limit, and this limit is called what? Differentiation of f of z. Consider the function f of z equals to 4x plus y plus I into minus x plus 4y. That means real part 4x plus y and imaginary part minus x plus 4y. We have to find out the partial differentiation of f with respect to complex variable z. That means we are given f of z equals to what? 4x plus y plus I into minus x plus 4y. So first real part will be u and imaginary part b. Just considering this, u equals to this and b equals to this one. Now f of z plus del z. If we increase z values to del z, then functional value what will be? F of z plus del z. This, and difference between ordinate. Okay, we get this one. So this difference, ordinate difference divided by abscissa difference. So we get the slope. Slope means what? Del f by del z. This is the actually slope in geometrical interpretation. Now along real axis means what? X-axis. Remember it. Always remember that real axis means x-axis and imaginary axis means y-axis. So along x-axis, the variable increased what? X plus del x, but y constant. Remember it. So this is why along x-axis we have to always differentiate with respect to x, but y will be constant. And similarly along y-axis, x is constant, x does not change. Okay, but y changed up to y plus del y. This is why when we differentiate along y-axis or imaginary axis, then we have to take x as a constant. So in this along real axis, y will be del y will be what? 0, because y does not change, y is constant. This is why del y what will be? 0. That means increase of y, small increase of y will be 0, and del z equals to what? Del x. Just putting this, we get this one. So along imaginary axis, what will be? Imaginary axis, you must know there is no no increment in x. So z equals to x plus iy, x will be 0, and del z equals to what? So del x equals to 0, because there is no increment in x. Just putting in this equation, we get del f del z what? 4 minus I. Same result. Along x axis, same result. Along y axis, same result. But along y equals to x, that means the straight line which passes through the origin. Okay, this is the y equals to x. If we take y equals to x, then q can be taken as x plus x plus del x and y plus del y. So in this case, z equals to x plus iy, y equals to what? X. Just putting y equals to x. So 1 plus I. And del z what will be? 1 plus I del x. But del y equals to what? Del x from this. Just putting in equation 1, we get the actually same result. Now we will try to discuss another one, example 2. Suppose how to find the partial differentiation of this complex variable. This is the x cube y into y minus ix divided by x to the power 6 plus y square. If z not equal to 0, okay, but functional value f of z equals to 0 when z equals to 0, then discuss differentiation of f with respect to z, okay, at z equals to 0. Now along if z tends to 0 along the radius vector y equals to mx, thus the equation straight line which passes through the origin, okay, the straight line which passes through origin y equals to mx. If z tends to 0, then along this line we must know from the definition of differentiability, limit z tends to 0 f of that means functional difference divided by point difference along the real axis. So this ratio is the actually slope of that complex function f of z. So limit of that ratio is called differentiation. Remember it. So limit, just putting the f of z value. F of z value what? This. Okay. And f of 0 what? Equals to 0. F of 0 equals to what? At z equals to 0. Functional value what? 0. So z equals to what? X plus iy. This is the complex function. Now taking LCM, we get this one. Okay. So limit z tends to 0. I minus I, this x plus iy and x plus iy will be cancelled. Okay. So minus I x cube y and x cube. So just putting y equals to mx here. Y equals to mx. We get if x tends to since z tends to 0, and here also z tends to 0, but this transform to what? Y omitted. This is why only real axis exists. So this is why x tends to 0, because all x variable is present. That means real part of complex number is present. This is why x tends to 0. Z tends to 0, transform to what? X tends to 0. But putting the value of x, we get a limit 0. Okay. But along y equals to x cube, along y equals to x cube, we get just putting the values, we get minus I by 2. In different paths, we get different values of differentiation of f with respect to z. That means one is 0 and minus I by 2. In such case, the function is not differentiable at z equals to 0, because different values we got. This is why it is not differentiable. The limit along y equals to mx and the limit y equals to x cube will be same. Okay. If same, then limit exists, otherwise not. That means left hand limit and right hand limit must be equal, otherwise not, limit not exist. We are given f of z equals to absolute value of z square, but the modulus what? Modulus of z what? Root over x square plus y square. But squaring on both sides, we get x square plus y square. Absolute value of z square equals to what? X square plus y square. Since x square and y square are polynomial, so this sum is continuous everywhere. You must know polynomial function is continuous at everywhere. Remember it. So the absolute value of z square is continuous everywhere. Now that according to the definition of differentiation of complex function f of z, limit del z tends to 0 and functional difference divided by point difference along real axis. That means del z. So the differentiation, the putting the values of functional values at z plus del z, z plus del z absolute value whole square minus f of z equals to absolute value z whole square. So, but using the properties of complex number, z and conjugate complex number multiplication, what will be? Absolute value of z square. So we can write this like this, okay, using these properties of complex number. But remember this, that is the complex variable here. So just multiplying, we get this 4 item, and z bar will be cancelled. So we get only 3 terms divided by del z. So this divided by del z will be z bar, and this divided by del z will be del z bar, and this divided by del z will be what? This ratio. So if del z tends to 0 and this become 0, and this rate becomes del z bar del z. Now since del z tends to 0 and del z bar also what? Conjugate also tends to 0. If we transform to in polar form, del z equals to what? R cos theta plus I sin theta, and conjugate will be just take minus, okay, and this ratio will be what? This, and but we can write this one now by de Moivre's theorem. We can write this one. So cos theta minus I sin theta whole square. So this square means you must know by de Moivre's theorem, cos twice theta minus I sin twice theta. Since this ratio depends on theta, it means that different values of theta, and this has different values. So it means this ratio has different values for different z. Hence, the limit of this ratio will be differentiation. Okay, this limit does not tends to a unique limit when z doesn't equals to 0. Thus, from equation 1, it follows that the differentiation of f of z is not unique. Hence, f of z is not differentiable when z doesn't equals to 0. But when z equals to 0, then the differentiation equals to 0. Differentiation of f of z is 0. Okay, we have proved already. So we conclude that the function is differentiable at z equals to 0.